From the dawn of humankind, we have gazed up at the night sky in awe. The twinkling stars, a celestial tapestry, have captivated our imaginations for millennia. Ancient civilizations wove stories into the constellations, myths and legends passed down through generations. The cosmos, an endless sea of darkness sprinkled with points of light, both terrified and enthralled our ancestors. They observed the celestial dance of the planets, the waxing and waning of the moon, the regular rhythm of the cosmos. These early astronomers, through careful observation and deduction, laid the groundwork for our modern understanding of the universe. Their instruments were simple, their mathematics rudimentary, but their thirst for knowledge was no less profound. Today, armed with powerful telescopes and sophisticated spacecraft, we peer deeper into the cosmos than ever before. We've mapped billions of galaxies, each a swirling island universe containing billions of stars. We've witnessed the births and deaths of stars, the violent collisions of galaxies, the dance of black holes warping the fabric of space-time, and yet, for all our knowledge, the universe remains a place of profound mystery. The human drive to explore is deeply ingrained within us. Just as our ancestors crossed oceans and continents, driven by a thirst for discovery, so too do we venture into the cosmos. Space exploration is the ultimate expression of this innate curiosity, a testament to our desire to push the boundaries of knowledge and understanding. From the launch of Sputnik, the first artificial satellite, to the Apollo missions that landed humans on the moon, each step into space has been a leap forward for humanity. We've sent robotic explorers to every corner of our solar system, from the scorching surface of Venus to the icy plains of Pluto. These missions have beamed back breathtaking images and invaluable data, expanding our understanding of our cosmic neighborhood. But our exploration of space is more than just a quest for knowledge. It's a search for answers to fundamental questions about our place in the cosmos. Are we alone in the universe? How did life arise on Earth, and could it exist elsewhere? What is the ultimate fate of our universe? As we delve deeper into the cosmos, we gain a new perspective on our own planet. From space, Earth appears as a fragile blue sphere, a delicate oasis suspended in the vastness of space. The images of our planet taken by astronauts have profoundly impacted our understanding of our interconnectedness and the importance of protecting our home. The study of the cosmos also helps us understand our place in the grand scheme of things. We are, after all, stardust. The very atoms that make up our bodies were forged in the hearts of stars billions of years ago. This profound realization connects us to the cosmos in a way that few other things can. Beyond the familiar stars of our Milky Way galaxy lies a realm of unimaginable vastness. Here, scattered across the cosmic ocean, are billions upon billions of galaxies, each an island universe unto itself. These vast collections of stars, gas, dust, and dark matter are bound together by gravity, engaged in a celestial ballet that has unfolded over billions of years. Imagine gazing upon a dark, clear night sky, far from the city lights, where the Milky Way appears as a faint band of light stretching across the heavens. Now picture each tiny point of light within that band as not just a single star, but as an entire galaxy, teeming with billions upon billions of stars. The sheer scale of the universe, with its countless galaxies spread across unimaginable distances, is enough to boggle the mind. The light from these distant galaxies has traveled for billions of years to reach us, offering a glimpse into the distant past. When we study galaxies, we are looking back in time, witnessing the universe as it was when the light first embarked on its journey across the cosmos. This cosmic time machine allows us to piece together the history of the universe and understand how galaxies have evolved over eons. Among the most awe-inspiring galaxies are the spirals, their majestic arms swirling outwards like celestial pinwheels. Our own Milky Way is a spiral galaxy, a vast disk of stars, gas, and dust with a central bulge and graceful arms spiraling outwards. These arms are not static structures, but are constantly moving like ripples on a pond as stars and gas orbit the galactic center. The formation of spiral arms is a complex process driven by the interplay of gravity, rotation, and density waves. As gas clouds within the galaxy's disk orbit the center, they encounter regions of slightly higher density. These density waves act like gravitational traffic jams, compressing the gas and dust and triggering the formation of new stars. The bright blue stars that trace out the spiral arms are massive, hot, and short-lived. They burn brightly for a few million years before exploding as supernovae, seeding the interstellar medium with heavy elements that will eventually be incorporated into new generations of stars and planets. The spaces between the spiral arms are not empty, but are filled with older, redder stars, as well as vast clouds of gas and dust that provide the raw materials for future star formation. Spiral galaxies are just one type of galaxy in the universe's grand menagerie. Elliptical galaxies, as their name suggests, are smooth, oval-shaped galaxies with little gas and dust, and a predominantly older stellar population. They are thought to form through the mergers of smaller galaxies, their spiral arms disrupted by the gravitational tug-of-war. Irregular galaxies, as their name implies, defy easy classification. They come in a wide variety of shapes and sizes, often the result of gravitational interactions or collisions with other galaxies. These galactic encounters can trigger intense bursts of star formation, lighting up the night sky with the brilliance of newborn stars. Dwarf galaxies, as their name suggests, are much smaller than their larger counterparts. They are thought to be the building blocks of larger galaxies, gradually merging over billions of years to form the majestic spirals and ellipticals we see today. Despite their diminutive size, dwarf galaxies play an important role in our understanding of galaxy formation and evolution. Within the vast swirling galaxies amidst the cosmic dust and gas lie stellar nurseries. These are regions of intense star formation where gravity coaxes clouds of hydrogen and helium into dense clumps, igniting the fires of nuclear fusion and giving birth to brilliant new stars. Imagine a vast, dark cloud of gas and dust, light years across, its depths illuminated by the faint glow of distant stars. Within this cloud, gravity draws the material inward, slowly at first, then with increasing speed. As the cloud collapses, it fragments into smaller, denser clumps, each one a potential star in the making. As the clumps continue to collapse, their cores heat up, reaching temperatures of millions of degrees. At these extreme temperatures, hydrogen atoms, the simplest and most abundant element in the universe, begin to fuse together, creating helium and releasing tremendous amounts of energy. This nuclear fusion is the engine that powers stars, flooding the surrounding space with light and heat. Section 2, Stellar Evolution. Once a star ignites, it embarks on a journey through the cosmos, its fate determined by its mass. Smaller stars like our Sun live relatively long lives, steadily fusing hydrogen into helium for billions of years. These stars are the cosmic anchors, providing light and warmth to their planetary systems, nurturing the potential for life to emerge. Larger stars, however, live fast and die young. Their immense gravity creates intense pressure and heat in their cores, causing them to burn through their nuclear fuel much faster than their smaller counterparts. These stars shine brightly but briefly, their lives measured in millions rather than billions of years. As a star exhausts its supply of hydrogen, it begins to fuse heavier elements in its core, moving up the periodic table from helium to carbon, oxygen, and beyond. These fusion reactions release even more energy, causing the star to expand and cool, transforming it into a red giant. Section 3, Cosmic Cataclysms. The death of a star is one of the most spectacular events in the cosmos. For smaller stars like our Sun, death is a relatively gentle affair. As the star runs out of fuel, it sheds its outer layers into space, forming a beautiful planetary nebula, a glowing shell of gas and dust illuminated by the dying star's core. The core itself will eventually cool and fade, becoming a white dwarf, a dense Earth-sized ember that will slowly radiate away its remaining heat over billions of years. For massive stars, however, death is anything but gentle. As the star's core collapses under its own gravity, it triggers a runaway nuclear reaction, releasing an unimaginable amount of energy in a blinding explosion known as a supernova. For a brief moment, the supernova outshines an entire galaxy, spewing heavy elements into space, seeding the interstellar medium with the building blocks for future generations of stars and planets. The core of the star, crushed by the immense force of the supernova, can take one of two paths. If the core is massive enough, it will collapse into a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. If the core is not massive enough to form a black hole, it will become a neutron star, an incredibly dense object composed almost entirely of neutrons, packed together so tightly that a teaspoonful of neutron star material would weigh billions of tons. Section 1. Planetary diversity. Our solar system is a celestial ballet of diverse worlds, each a unique expression of the forces that shaped our cosmic neighborhood. From the scorched plains of Mercury to the icy plains of Pluto, our solar system is a testament to the incredible variety of planetary bodies that can exist. Closer to the Sun, the inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds sculpted by volcanic eruptions, asteroid impacts, and the relentless weathering of the solar wind. These terrestrial planets, with their solid surfaces and relatively thin atmospheres, offer a glimpse into the early solar system, when the planets were still forming from the swirling disk of gas and dust that surrounded the young sun. Further out, beyond the asteroid belt, lie the gas giants, Jupiter and Saturn behemoths of hydrogen and helium, with swirling storms that dwarf our entire planet. These gas giants, with their deep atmospheres and powerful magnetic fields, are like miniature solar systems, with dozens of moons orbiting them like planets around a star. And then there are the ice giants, Uranus and Neptune, blue-tinged worlds rich in methane and other ices, their atmospheres whipped by supersonic winds. These distant giants, with their tilted axes and strange magnetic fields, hold clues to the outer reaches of our solar system, where the sun's influence is weak and the temperatures are frigid. For centuries, astronomers wondered if our solar system, with its unique collection of planets and moons, was alone in the universe. Could there be other stars out there, harboring their own planetary systems, perhaps even worlds similar to our own? Today, thanks to advances in telescope technology, we know the answer is a resounding yes. Exoplanets, planets that orbit stars other than our sun, are not just a figment of science fiction, they are a reality, and they are more common than we ever imagined. Using a variety of techniques, astronomers have detected thousands of exoplanets, ranging in size from small rocky worlds like Earth to massive gas giants larger than Jupiter. Some exoplanets orbit their stars in close, scorching orbits, completing a year in a matter of days. Others are locked in distant, frigid orbits, taking centuries to circle their stars. Some exoplanets orbit their stars in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on the surface, a key ingredient for life as we know it. The discovery of exoplanets has ignited our imaginations, fueling our dreams of finding another Earth, a twin planet teeming with life. The search for life beyond Earth is one of the most profound scientific endeavors of our time, a quest to answer one of humanity's oldest and most fundamental questions. Are we alone in the universe? While we have yet to find definitive evidence of extraterrestrial life, the search is ongoing, and the possibilities are tantalizing. Astronomers are developing new telescopes and techniques to study the atmospheres of exoplanets, searching for telltale chemical signatures that could indicate the presence of life. The search for life beyond Earth is not just about finding aliens, it's about understanding our place in the cosmos. If we were to find evidence of life elsewhere, it would fundamentally change our understanding of our place in the universe, demonstrating that life is not a fluke, but rather an inherent property of the cosmos. The dream of space travel, of breaking free from Earth's gravitational pull and venturing into the cosmos, is one that has captivated humanity for centuries. From early science fiction writers to visionary scientists and engineers, the idea of journeying to other worlds has inspired countless imaginations. In the early 20th century, the dream began to transition from fiction to reality, as pioneers like Konstantin Tsiolkovsky, Robert Goddard and Wernher von Braun laid the theoretical and practical groundwork for rocketry and spaceflight. Their work paved the way for the development of powerful rockets capable of launching payloads and eventually humans into space. The dawn of the space age arrived on October 4, 1957, when the Soviet Union launched Sputnik 1, the first artificial satellite, into orbit. This momentous event marked a turning point in human history, signaling the beginning of our journey into the cosmos. The space race was on, with the United States and the Soviet Union vying for supremacy in this new frontier. On July 20th, 1969, the world watched in awe as American astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the moon. Their historic mission, Apollo 11, was the culmination of years of research, development, and testing, a testament to human ingenuity and determination. One small step for man, one giant leap for mankind, Armstrong famously declared as he stepped onto the lunar surface. His words echoed around the globe, capturing the profound significance of this achievement. The moon landing was not just a technological triumph, it was a defining moment for humanity, a symbol of our ability to overcome seemingly insurmountable challenges and achieve the impossible. The Apollo missions returned a wealth of scientific data and lunar samples, revolutionizing our understanding of the moon's formation, composition, and history. They also inspired generations of scientists, engineers, and dreamers, igniting a passion for space exploration that continues to this day. The end of the Apollo program did not mark the end of human spaceflight. In the decades that followed, we have continued to push the boundaries of space exploration, sending robotic probes to every corner of our solar system and beyond. The International Space Station, a marvel of international cooperation, has been continuously inhabited by humans for over 2 decades. This orbiting laboratory has served as a platform for groundbreaking research in a variety of fields, from medicine and biology to materials science and astrophysics. Looking to the future, space agencies and private companies around the world are developing ambitious plans for human missions to Mars and beyond. These missions will not only expand our scientific knowledge, but also test the limits of human endurance and ingenuity. As we stand at the precipice of a new era of space exploration, it's worth reflecting on the incredible journey that has brought us to this point. From the earliest stargazers to the astronauts who have walked on the moon, our quest to understand the cosmos has been a testament to the power of human curiosity, ingenuity, and the relentless pursuit of knowledge. We've come a long way from those early days of gazing up at the stars in wonder. We've mapped the cosmos, unraveled the mysteries of stars and galaxies, and discovered thousands of planets beyond our solar system. We've sent robotic explorers to distant worlds and built a permanent human presence in space. But our journey is far from over. The universe is vast and full of mysteries yet to be solved. Dark matter, dark energy, the search for extraterrestrial life. These are just a few of the cosmic enigmas that await us. And as we continue to explore, we can be sure of one thing: the universe will continue to surprise and amaze us. So the next time you find yourself under a clear night sky, take a moment to look up and contemplate the vastness of the cosmos. Let the twinkling stars ignite your imagination and inspire you to learn more about the universe we inhabit. For in the grand tapestry of existence, we are all connected, from the smallest atom to the largest galaxy. Space exploration is more than just a scientific endeavor, it's a reflection of who we are as a species. It speaks to our innate curiosity, our desire to push the boundaries of knowledge, and our yearning to explore the unknown. It's a legacy we pass down from one generation to the next, a gift that will continue to inspire and amaze for generations to come. Keep looking up, keep asking questions, and never lose your sense of wonder. The universe is waiting to be explored.